Continuing our discussion on hypothesis tests in part 3, the critical value separates a critical region from the non-critical region. We'll be looking at tests that either use the normal distribution or the student t-distribution to start, at least for chapters 8 and 9. When we move into chapter 11, we'll pick up 2 new distributions that we'll use for special hypothesis tests in those chapters, but the ideas are all the same. The critical value is going to be a value that's coming from the corresponding distribution that we're using for the test. So we'll use a standard normal distribution for proportions, just like we used the standard normal to get our z alpha over 2s for the confidence intervals. So we'll look at standard normal for proportions and a t-distribution for means. Exactly the same distributions that we were using for our confidence intervals. We have a critical region. Sometimes it's called the rejection region. And this region is going to be a range of values that'll indicate a significant difference with that null hypothesis. The data that we've gathered indicates there is a significant difference between our population parameter and whatever value we have for that null hypothesis. The difference is too big, and we should reject the null hypothesis. The critical region is always the smaller region in the diagram, and I have some pictures in a little bit to show us. And then the non-critical region, or the non-rejection region, this region is the range of values that indicate the difference was probably just due to chance. It's close enough to what the null hypothesis is saying, so we shouldn't reject the null hypothesis. And the non-critical region is always the larger region in the distribution. When we're running a hypothesis test, we have significance levels, and typical significance levels are 0.1, 0.05, and 0.01. We could have others, but here in an example, if alpha is 0.1, there's 10% chance for a type 1 error. So this is where we directly control the probability of a type 1 error, is with our choice for significance levels. In hypothesis testing, the alternative hypothesis determines what type of test we conduct. So we have 3 different scenarios here for less than, not equal to, and greater than. So the null hypothesis we always assume to be true unless shown otherwise. The alternative hypothesis determines our critical regions and whether we're doing what's called a one-tail or a two-tail test. And you can see what I mean by that with the pictures. In the first example, we have the proportion is less than a number or the mean is less than a number. I'm using both of them just so that you know we're looking at alternative hypotheses on either a proportion or a mean, and that less than is our alternative hypothesis. So we're going to have a left-tailed test. In the middle sits our mean or our proportion. And so if we have something less than that, we're looking at getting a test statistic possibly somewhere in the left. So we have this idea of a left-tailed test. It's a one tail. These ends here are called tails. And we're only looking at one of them for our critical region. And you can see here the red is our critical region and our green is our non-critical or our non-rejection region. Suppose we get a test statistic from our calculations for the hypothesis test. So the hypothesis test will have some formulas that we'll have to use. We'll plug it into technology. Remember, our focus is interpretation and understanding rather than just rote calculations. So in the test statistic, we could have a test statistic that falls here. If the test statistic falls in our non-critical region, we would not reject the null. But if our test statistic falls in the critical region, we would reject the null. The critical region is that probability of a type 1 error. And if our test statistic falls in that region, the differences between our null hypothesis and our data is significant. It's not really up to chance. Whereas if it's over here in the non-critical region, that test statistic likely is there because of chance. They're slightly different, but not different enough. Okay, I say all of this to say that we'll have our distribution. We'll determine the critical region based on whatever our significance level is, alpha, and this area is alpha for our critical region. We'll calculate a test statistic and then put that test statistic on the number line in relation to where this critical value is and make a conclusion. That's how we would do the traditional method for hypothesis tests. If our alternative hypothesis is a not equal to, we do something called a two-tailed test. In a two-tailed test, we take that alpha and we divide it into two and we put half of the probability on either side. So we'll have two critical values that we're looking at in a two-tailed test. In the other one-tailed test, here's a right-tailed test. You'll notice we have greater than, and we only have one critical value with alpha being the area in that tail. And we call it a right-tailed test because we are looking at greater than, which is to the right of 0. We can take all of this information for hypothesis tests and put it together in a procedure that we can follow. And as you practice more and more, the procedure becomes more natural, and we'll be doing hypothesis testing for the rest of the semester. Chapter 8 all the way through Chapter 11, we're doing hypothesis tests. So the first step, identify the claim. Identify what the claim is and express it in symbolic form. We identify the claim and write it in symbolic form. And then we write the symbolic form that must be true if the original claim is false. So we're creating that dichotomy between the null and the alternative hypothesis. The one with equals is our null hypothesis. The one with not equals is our alternative hypothesis. A reminder for our null hypothesis, we could also have greater than or equal to or less than or equal to. Some textbooks and some studies will use those symbols for our null hypothesis. Once we have our hypotheses, then we can select the significance level. When we're practicing here with problems in class, sometimes the significance level is given to you. Sometimes it's not given and you have to choose it yourself. But we want to select a significance level, that's our alpha, based on the seriousness of a type 1 error. If the consequences of rejecting a true null hypothesis are severe, we want alpha to be small. We don't want the probability of a false positive to be high. We usually use 0.05 or 0.01. Sometimes we've seen 10%. So we want to pick something small. 10% or smaller in general is our significance level. And then we identify the test statistic. So we choose which test we're doing based on which parameter we're testing and what we're given or what we have. And then we can calculate our test statistic. We'll see some formulas in just a minute. In the next step, find values. The values depend on what type of test we're doing. If we're doing the p-value method, we get the test statistic and the p-value. We draw a graph showing the test statistic and the p-value. We compare the p-value to alpha. The p-value is just a probability. The probability of the test statistic itself. What's the probability that the test statistic actually occurs? If we're doing the critical value method, we would find the value of the test statistic and the critical values, and the critical values come from our alpha, our significance level. And then we draw a graph showing where the test statistic and the critical values are, and that critical region. I'll do examples of both in a future lesson so that you can see the difference between them. Technology makes the p-value method a little bit easier in comparison to the critical value method. But the critical value method was really popular before technology took over. For me, in my class, I don't care which method you use. You can use whichever one makes the most sense, but I'll show both so that you can see the difference between them. Once we find the values, the test statistic, the p-value or the critical value, depending on which method we're using, then we make a decision. For the p-value method, we compare that p-value, that probability, to alpha. We reject the null if the p-value is smaller than alpha, if our probability is smaller than this threshold that we're given for alpha, the significance level. We fail to reject the null if the probability is higher than alpha. Probability is bigger, so it's more likely to happen. In the critical value method, we reject the null if the test statistic is in the critical or rejection region, and we fail to reject the null if the test statistic is not in the critical region. And then the last step, we restate the decision in non-technical terms. We have to take out HO or H1. We need to put it back into the context of the problem, the context of our research. So we'll restate this previous decision, whether it's reject the null or fail to reject the null, in non-technical terms, and address the original claim, which, remember, the claim could be either the null or the alternative hypothesis. Let's break down step 5. So for step 5, determining the test statistic, we have a proportion. We'll use the normal distribution. We have to make sure that n times p and n times q are greater than or equal to 5 so that we know we can use the normal distribution to approximate the binomial that comes up with the proportion. And we have a formula for our test statistic here. P hat is our sample proportion minus p, which is coming from our null. So that'll come from our null hypothesis. And then square root pq over n. And again, p is our population parameter. So our null hypothesis is going to give us that. And n is our sample size. We could plug in the numbers that we have and calculate that. Or we can use the corresponding functions on Google or Excel to give us the test statistic or the p-value. It actually turns out that Excel and Google, when you use the corresponding formulas for the technology, will give you back the p-value for the tests. And I'll show you in the examples specific to these different situations how to use the technology. The mean, when we don't know the population standard deviation and we have a normally distributed population, or n is greater than 30, we can get a test statistic there. So we will primarily be using the proportion and the mean with the t-distribution. We have a statistical test for the mean using the normal if we know the population standard deviation, but we are not going to focus on that one for the same reasons already mentioned. If we know the population standard deviation, we likely already know the mean. Do notice the similarities between these two test statistics in calculation. The t-distribution uses the sample standard deviation. The z uses the population standard deviation, but it's the same structure. In step 8, in wording our conclusion, remember that we make our decision based on the null hypothesis. We either reject the null or we do not reject the null. If we reject the null and the claim is the null, then there is enough evidence to reject the claim that, and whatever the claim is, we would restate in non-technical terms. If we reject the null but the claim is the alternative, then there is enough evidence to support the claim because the claim's the alternative. Notice the difference here. If we make a decision to not reject the null and the claim is the null, there is not enough evidence to reject the claim. Remember, we never say accept. We're not that confident when we're using statistics to say accept. We only say reject or fail to reject. And if we do not reject the null, but the claim is the alternative, we don't have enough evidence to support the claim. This conclusion wording is a guide for how to write statistical conclusions. And then one last definition. In a hypothesis test, the p-value is the probability of getting a value of the test statistic that is at least as extreme as the test statistic obtained from the sample data, assuming that the null hypothesis is true. Big picture, the p-value is coming from the test statistic. It's the probability for the test statistic occurring given that that null hypothesis is assumed to be true. And then the last bit, just know that there is a relationship between hypothesis testing and confidence intervals. If we reject a null hypothesis for a hypothesis test, the confidence interval for the mean using the same level of significance will not contain the mean in the null hypothesis. Similarly, if the null hypothesis is not rejected, the confidence interval using the same level of significance will contain that mean. So there's a direct relationship between hypothesis testing and confidence interval, and that'll conclude our introduction to hypothesis testing. Check out the next lessons for examples and how to go from start to finish for a proportion and for a mean. These lessons on the basics of hypothesis testing will follow us throughout the rest of the semester. So we'll see this stuff a lot in the future. We'll continue to use this process for hypothesis testing from chapter 8 all the way through chapter 11.